So that's the so-called direct term. Whereas the other term, you can't do that because if you pair up the 1 and the 1, x1 here, you see that the label here is 3 or 4. Okay? So in a sense, it's like the particle 4 changes at position x1, it particle 4 and then it changes to particle, it changes from n equals 4 to n equals 3. Similarly, for x2, it changes from 3 to 4 the other way around. So this is like exchanging. Okay? If you think of it like this, x1, x2, originally I have x1, let's say this is originally, x1 is state n equals 2, and then it turns into n equals, sorry, x1 here is at n equals 4, x1 is at n equals 4, x2 is at n equals 3, and then later on it becomes x1 is n equals 3, and x2 is n equals 4. So basically they swap around. And that's the reason why it's called exchange. This bit here. Okay, this bit here is the direct term. So the I integral with all this mass here is the direct term, and the J integral, which can have minus or plus sign, is the exchange term. Okay, so that's the question 4. I think that's the end of it. And so you can see that depending on whether you have whether J is positive or negative, you can raise or lower the energy, depending on whether you use the triplet state or the singlet state. Okay, so the more physical significance is that sometimes even though the interaction doesn't have any spin bits in it, okay, this is just a standard Coulomb interaction, nevertheless the answer seems to prefer one spin state compared to the other, and it all boils down to how the wave function works. Okay, and so it's a sort of indirect effect of the wave functions trying to stop two particles being in the same place. Because if you have the anti-symmetric combination, you can't put two particles in the same place. So that tends to make the particles want to avoid each other. Sorry. Oh, excellent. Yeah, the other ones were really alright. I don't know how that happened. Must be someone else who asked for it and they took forever to come. Right, okay. So any other questions? So basically, some physical significance is that the Coulomb interaction don't want two particles to be close together, let alone on top of each other. And in the anti-symmetric spatial combination, look, if you have the anti-symmetric spatial combination, minus 5, 3 of 2, 1, 2. If now I say I try to put two particles in the same place, that means I change both of these into ones. You see that this is just 0. So that's basically Pauli principle. If you put two particles in the same place for the anti-symmetric spatial wave function, you can't get that. But that's good news if you have a Coulomb interaction, because Coulomb interaction will cause a lot of energy if you try to put two particles in the same place, right? If you have x1 equals x2, this Coulomb energy is in fact infinite. Okay, so that's the physical significance of why it is that what it really is telling you is that the anti-symmetric spatial wave function is good for the Coulomb repulsive interaction. If you have it the other way around, if this is if this interaction is actually negative, like one particle is has positive charge, the other one is negative charge, then it will be the other way around. Okay. Any other questions about this? There are some tedious bit that if you work it out carefully at home, then hopefully you can reproduce it in the exam. So do it now, and then this is in your bag, basically. Yeah.
Question 4, part C.
But be careful, okay? Sometimes, like question 5 in the hydrogen atom, there is a spin part, and then you have to be careful. And don't drop that. Okay, so that's question 4. Okay, we can either break or we can just quickly, well, we can just continue finish this in half an hour or so. Break or not? No, break.
Break.
Keep going, yes?
Oh.
Okay, so question 5, what, so C and D.
There's no stopping the quantum
Okay, it is quite, yeah, okay, so this is a hard question because we didn't give you the wave functions. And probably, I can't guarantee, but you should really recognize anyway what exactly the wave function should look like, even if you don't know the exact form of the wave function. So let me just drop some stuff out. Okay, so this is question 5C, and this is basically about hydrogen atom. And the hydrogen atom and the labels N, L, ML, and S, MS. Well, hydrogen atom has one electron, so S is a half, spin half, because it has one electron. So you could have just written as S with a half, it doesn't really matter. But basically the wave function, what it is basically made up of the, in real space, X, let's call it R notation. The wave function is in fact, well, this is what you usually call ML, ML, R, and then you have some part, some state, the spin part. And that part is made up of, so this is the back part. This part is made up of, I hope you remember, but in the solution of the hydrogen atom, it's made up of the radial part and the angular bits. The radial part is R, which depends on N and L. So this is the radial solution of the radial equation, and then the other one is the spherical harmonics, YL and L. And this depends on the angles only, theta and phi. So that you need to know more or less. Okay, you won't need, well, if needed, you will be told what these wave functions look like. These ones, you should at least have some idea that YLMs looks like there's a bit which deals with the angle phi. That is the bit that is straightforward. It's just e to the im phi. Whereas the theta bit is more tedious. It's this Legendre polynomial. And it's, I think, if I remember right, I wrote it as something like this. I can't remember now. And it depends on cos theta, in fact. So this basically means that this is a polynomial, like x, y, or x squared, x cubed, and you have to put x equals cos theta, so it will be cos theta squared or something like that. So it basically looks like that, and I say it looks like that because there's a normalization in front of typically. And so that's what is needed. And so if I have this perturbing operator, which is this L dot S, then I have to write out the whole messy thing. It's kind of related to the one of the homework problem sheet, right? I think you should go back on the selection rule problem sheet. I forgot which number it is, but it's the selection rule problem sheet. Okay, so I have to compute. So it didn't say it, but it says energy correction to the state blah blah blah. It's really a first order perturbation theory formula that you're using. Okay, first order energy perturbation theory. Okay, so I basically need N, L, M, L, S, M, S against the perturbing operator, which is A over R cubed L dotted into S. Okay, so now we have to look for something. Now we have to separate out the bits and pieces. So this is the modulus. This is the radial thing, not the full vector. This is the radial coordinate out. And so now you have to write it out carefully. So, okay. So now you do care about the spin wave function because I have S operator here. S will act on the spin part of the wave function, or more accurately, the spin cat or bra. So, but first of all, the point, again, this is it looks as if it's tricky because I have L dot S, but in fact it's not as bad as you think. In this case, okay, because this state has the same MS and the same ML on either side for the bra and cat, then there's a trick. Okay, L dotted into S, what is it? It's L x S x plus L y S y plus L z S z. Now this bit is nice because S z acting on this stage gives me the MS, right? S z acting on this stage gets me MS times H bar. This gets me ML times H bar. So I know how LZ and SZ acts on the stage, but I don't know how to do this. Or do I? Well, actually, there is a way, and this is why we introduce all these raising and lowering operators. Okay, you might remember L plus or minus is Lx plus or minus ILy. Yes, so these are the raising operator, and importantly, L plus acting on a state with ML gets you something which is ML plus 1. It raises that quantum number. It doesn't change the L actually. L is the same. But it changes ML. It raises it by 1. Okay? So if I rewrite Lx instead L plus L minus, and that's a factor of half, it really doesn't matter that much. And Ly will have a factor of 1 over 2i, then there's a minus sign, it doesn't really matter. But for this purpose, Lx is basically L plus and L minus. And look at this, okay? If I put Lx between L and ML, and L and ML on the other side also. So I'm isolating out the angular momentum bits of the wave function just so that I can concentrate. If you like, you can stick back all the other bits too, but I'm just isolating out the relevant quantum numbers. That just becomes L, ML. Lx is L plus L minus divided by 2L ML. I can put the half outside, it doesn't matter. So L plus, so this means I have to add L plus on this state. And I'm not going to do it carefully because I don't need to. L plus acting on the ML gets me a state which is L, ML plus 1. That's L plus acting on that, yes? And then I also have the other one, which is that L minus acting on ML gets me ML minus 1. Okay, well, the Does everyone see where I get this from? Because I have L plus here acting on this state. So this means that I act on this and add L. Okay, so L plus acting on this state. I raise ML by 1. And then I add the other bit, which is L minus acting on this state. I subtract it. So this angular momentum goes down by 1. Okay, and I had this bothered to write out the normalization factor, because there should be a normalization factor. When L plus acting on this state, it becomes ML plus 1 with some normalization, which involves ML and all that crap. But it's not important. Why is it not important? It's 0, okay? At the end of the day, if this number is not the same as that number, that has to be 0. Okay, so that's why this acting on that state gets me 0, and similarly I can do the same thing for Ly. Ly just changes the sign of this minus and there's an I then. Okay, so is that clear why only Lz and Lz enters? Now, if you have Lz and Lz, then all I need is basically just so that basically is the hard work done, okay? So I now repeat what I said, N, L, M, L, S, M, S, with these thing, A over R cubed, L dotted into S. Now I no longer have to do the full L dotted into S, I just need LZ as Z. So I can replace that by LZ and SZ, okay? Okay, so that makes life a lot easier, and you can now do this calculation to finish off. Okay, so this now I have to unpack everything, right? Because I have the radial part and so I have the R, and this is spherical polar, so please do not forget there's an R squared. I have d theta sine theta, this is 0 to pi, and then I have d phi, 0 to 2 pi, that's standard spherical polar. I put the A outside because I don't really, this is just a number. And then I have, well, this is just a number also, 1 over R cubed. These kinds are running out. So I have 1 over R cubed coming from the 1 over R cubed. And now I have to put all the R and L's. I have R and L star of R, Y, L and L star of theta and phi. So the orbital part. And then I have the spin part, which I'll write later. And then I have R and L, R, Y, L, and L of theta and phi. Okay, I've just written out all the previous R and Y for each of these guys here. This brown here gets me the star thing, that here gives me that thing. And now I have to look up what to do with LZ and Z. But we've done that. Okay, so if I look at just the L, ML, and LZ, SZ bit, that gives me what? That just gives me the LZ, takes out the ML, okay? Oh, and I also have S and S, sorry, I need that too. And the SZ gets me the MS. And I have H bar squared. Okay, and then I have these states. and that's just 1 by orthonormality. Okay, so doing the LZ part, yeah, just gets me the ML and MS. So that's, this is from the spin part, spin and angular momentum, orbital angular momentum. Okay, sorry, I mean to write it. ML MS H bar squared. Okay, so that's basically the answer. I mean, I didn't give you the, well, the next part is to calculate the integral. So, okay, so this is delta E, is this thing here, the quadratic operator with these states. And basically, it says that it should write out the integral. So basically, this whole mass here, let me write H bar squared over here, including the H. That's the what's lambda and L. Okay. So this whole mass here is lambda and L. No, sorry, NL times NL and MS. So this whole big integral here, including the H bar squared here, is what's called the lambda NL. Okay? So that's part C and part D. And part E is actually doing the integral, and you have been given the form of the radial wave function. Now, I didn't give the what happens to the YLM. Why not? Why didn't I give you the YLM? Yeah, but here you have to do an integral. So why didn't I give you the form of the YLM?
Is it because they're not?
Because once you integrate it, it gets to 1 if you have normalized your wave function properly. Okay? So the point is this: the YLMs are normalized up. Okay? What does that mean? That means, let me write it here. That basically means that my d theta sine theta d phi of YLM star theta phi with YLM theta and phi is just 1. Normalized. Okay? Be careful, it has to be the same LMs, otherwise you get 0 by orthonormality, and you have the same theta and phi here. And then you have all this much there. And so I can then simplify this whole thing further, because I can pick out this bit, I can pick out this bit, and I can pick out this bit and this bit. Okay, so all the theta and phi bits I picked out as blue bits, and that gets me 1. So all I'm left with is A, dr, r squared. So all this bit, after I've done the integration by using this condition, this normalization condition, all I'm left with is 1 over r cubed, and then r n l star r n l of r. Those are the remaining bits, these bits, this bit, this bit, and then I have h bar squared, and then I have ml and ms. So this whole thing here is, this whole thing here is lambda nl. And then in part E, you just substitute in the form and do the integration. It's a bit tedious. I don't know if you can read I did it there in the solution. And it's a bit tedious, and you have to be very careful. So you for this guy here, RNL is e to the minus r over 2a times r over a, and there's some normalization which I won't bother. I just want to sketch what's going on. So you get this, and actually this is a real wave function. So the star doesn't make any difference. So at the end of the day, you have the r squared cancels partly this. You have 1 over r away. Something's gone wrong. Yeah, no, it's correct. And then I have r over a for each r. So I have one from here and one from here, so that's squared. And then I have e to the minus r over a, because I have got two of them. E to the minus r over 2a times e to the minus r over 2a, that gets me e to the minus r over a. And that's the integral you have to do, plus some stuff out here, okay? And as you can see, this is an integral which is not too bad. Some stuff here. I have r times e to the minus r over a. And the trick I did in the solution was to differentiate the integral. Differentiating with respect to a, or 1 over a. But you could do it by parts or any way you want to. Yeah? Okay? So I won't bother doing that. But yeah, okay? Whoever asked this, is that okay? Any other questions? Yeah?
This is just regarding the paper in general. Do we get some of the integral identities?
Yes, probably. I mean, not all. For example, some simple integrals you should know how to do, like integral of sine x or sine squared x. Okay? And sometimes you get tedious ones. Well, I don't know. I mean, if you get tedious ones like sine nx and sine mx multiplied together, you might just give you the integral. Because at the end of the day, and the Gaussian integrals, yes, you will be given. Because that's. But really, if you're going to do fourth year course, you should memorize these Gaussian integrals, the basic ones, and then you can derive all the others. Yeah, so okay, so good luck and try to stay calm. Yeah, when you look at it. It may not look like something you're trying to solve the solution. But then on the converse side, if a question looks like something you're trying to
The calm is not staying.
Like he doesn't know about it.
Was the calm ever here to begin with?
I mean, if you want answers to past questions, either email me or come and see me, because I don't want to put out all the solutions. Most of the time you get the answer there in the question anyway. But if you want to check something, do it and come to see me and ask.
It's like the new Will Metals. This is blunder. Yeah. After it comes up the camera. Oh god.
I think what he needs to